Hello guys, thanks for watching my video. So in this video clip I'm going to show you how to uh, make a tube configuration file for testing recitifiers. Um, um, for recitifiers, there's basically two types of the rectifiers, the half wave rectifier or a full wave rectifier. Half wave rectifiers are like early made in the early 30s. So tube type, the tube is like 81 is a single diode. It's a half wave rectifier. And most vacuum tube rectifiers we use today are full wave rectifiers, which means that it has two diode or two diode in one package. So the most famous one is probably tubes like 5U4G, something like that. So in previous video, I show you how to design the wiring part and the graph display part. And so for rectifiers, we first provide information on the wiring. Okay, so this is the PCB menu for etracer. You can download it from the etracer website. So in this section, it actually tells you how to wire the DUT for testing. This is the output for on the etracer PCB, and this is the device under test. So basically, we connect HV1 and HV2 to the DUT is a 5Z3. It's equivalent to a 5U4 with a different pin out. This is a 4-pin UX4 socket, and 5U4G is octo. It's an 8-pin socket. And okay, so internally, the rectifier is like a diode, ideal diode with a resistor connected in series. So it's like this. So what we are what the wiring does is we send the voltage here and test the current through this device, through this diode. And for tubes like 5Z3 or 5Z4, 5U4G, it's they are direct heated rectifiers, which means the filament is a cathode, and inside the etracer PCB, the heater, one side of the heater supply is connected to the ground with a 1.1 ohms resistor. So when we send the test voltage here, we can then measure the currents. It forms a loop, and we can measure the current for each voltage. Okay, so there's also variations of rectifier. This is the direct heated rectifiers, and we also have the tubes like GZ34. This tube shares the same socket as 5U4G, but the heater, the cathode is actually indirectly heated. It has a separate cathode. It has a cathode separated from the heater, but the one side of the cathode is actually tied to the heater, so the connection is the same for this tube. And as you can see, heater is supply connect to the filament here, and the cathode is tied to ground through the heater supply. And there are also other type indirectly heated rectifiers like 6CA4. This type of tube, it has a separate the cathode and the filament are not tied together, and the reason is the rectifier. This way, the rectifier can share the filament supply with other small signal tubes. For example, if this filament supply is 6.3 volt, the machine or the amplifier can share the 6.3 volt winding with other small signal tubes like 12AX7. So for this kind of rectifier, we need to connect the cathode to the ground output of the etracer PCB. Okay, so basically these are the how we are going to connect the device under test. So we need to write it down here. So for example, let's say we are going to design a configuration file for PHYU4. So we can open the data sheet for a PHYU4. Here I am going to use the one from GE. Okay, so so here we can see the basing diagram. So this is basically the connection inside the tube, and we can see pin 4 and pin 6 are tied to the plates, the anode of the diode, and the pin 2 and pin 8 are two ends for the filament. So we can put it on here. 4 and 6, plate 1 and plate 2, plate 1, plate 2, and 2 and 8 are heaters, heater 1. Okay, if you remember what I said in the previous video, these are only for the user to connect to the wire. It does not do the wiring for you. The user has to do the wiring. So heater 1 is connected to heater 1. Heater 2 is okay. So the order is not important. So you can say, okay, I want to connect this guy to heater 2 and this guy to heater 1. That's totally fine. And plate 1 and plate 2 connected to HV1, HV2 is explained here in this diagram. So next thing we need to do is like I explained in the previous video, the setting here under these three tabs and the setting here are the configuration that's going to control the hardware. So here we need to set up the heater supply for this rectifier PHYU4, and in the data sheet it's 5 volt AC or DC, and with a current reference current of 3 amp. So we can put the 5 volt here, reference 3 amp, and that's the configuration for the heater. Okay, so next we want to configure the full scan, and we need to configure. Actually, when we set up the display range for the plot, we usually refer to this configuration for full scan. And for rectifier, we want to measure the plate voltage versus plate current. So we need to find the curve for that. Okay, so this is a curve in the data sheet, the plate voltage and the plate current. So this is a curve we're going to draw. This one is probably, let's use the RCA one. There's on the website you can find a lot of data sheets. Some of them are not very detailed. So when you design a tube configuration file, please find the go through the data sheet and find the most detailed one and use it. Okay, so next one we are going to configure is PMUX, because without setting the PMUX, the software will not start. Pmax is the set out the criteria that for the stop criteria for the curve tracing, and when the power is calculated as a plate voltage times the plate current. So it's when the power exceed this guy Pmax by 1.5 times, the software will stop because it's already over the safety operation point for this tube. So it's important to set out the Pmax. And how do we find Pmax for rectifier? We find the maximum current of this tube. So the maximum rating for a 5U4, the current is 300 milliamp full load, something like that. And if you check the amplifier circuits, usually this guy is designed at like 250 milliamp per tube. So let's say if we use 300 milliamp and then we come to this curve, 300 milliamp, we can see the plate to cathode voltage is like 454 volts. So let's say it's 54 times 300 milliamp. It's 13.5 watts per plate. So we can fill in this number. We can fill in this number here, 13 or 15. The number of the 1 or 2 watts difference is not important because basically etracer is testing the tube impulses, so it will never exceed the maximum power rating of the tube because the measurement is done in pulses, so it's not continuous, so it won't damage the tube. So even you configure this guy at a higher value, it's not a big deal. And the software only check the maximum power for HV1 for the first only for HV1, so you don't have to set out the HV2 Pmax for HV2. Okay, now then we need to configure the range for the full scan. So we have to come back to this graph, and we know that the maximum current is 300 milliamp. So we're only interested in this range. So we can see we are only interested to about 50 volts of plate to cathode difference. And also we know that the maximum capacity of etracer is 300 milliamp. So anything beyond 300 milliamp cannot be measured by etracer. So here we can set maximum to 50, 300 milliamp. We want to check the because it's a full wave rectifier, so we want to check both sections. So we turn the right axis on, and we need to turn on HV2, and HV2 has the voltage on HV2 has to follow HV1 at 100%. Okay, so let me download the configuration file for 5U4. Okay, I put the 10 watts here, but it's okay. It's not that important because like I said, the etracer stop at 1.5 times of this guy, and under usual condition we don't run the 5U4 at its full capacity, current capacity. Okay, so HV1 we test from the HV1 start from 0 end at 50 volt, 0 volt to 50 volt at the step of 10 volt. At the step you can decide, you can say, you can probably use 5 volt, 10 volt, 20 volt, it's up to you, but the bigger the step, the shorter the test time, the finer the step, the longer, the smoother the curve, but the longer the test time. So it's a trade-off. So usually 5 or 10 test points is reasonably good enough. Okay, so this is this complete the setup for full scan, and we already, and the graph is matching the setting of the full scan tab. For rectifiers, we only set up the quick scan and full scan. We don't do the corner test on rectifiers. Okay, now we need to configure for quick scan. And what else? Yeah, okay, 100%. I mentioned that. So it's link HV2 output follows HV1, and the linkage is 100%. So it's 1-to-1, which is desired for testing full wave rectifiers. Okay, here we come to the quick scan. So quick scan is we need to select the point to measure the parameters. For rectifiers, what's interested us is the current as voltage and the AC resistance. Okay, so which point to choose? Sometimes you can find the recommended test current, recommended condition in the table. Something like, for example, I don't know, like 275 milliamp, 300 milliamp, that kind of stuff. And what I did is I just pick a point from this curve, and which I think makes sense, because for example, for a 300B stereo 300B, each 300B draw approximately 80 milliamp. And for the driver circuit, it's probably 20 milliamp. So the one channel is 100 milliamp. So two channel 200 milliamp, which is pretty much the current the ballpark for the current used for drew from a 5U4. So what I picked is the current of 200 milliamp. So for quick scan, we need to fill in the reference values here, because once the parameters calculated, the major data will is measured. The major data will appear here, and the percentage will be calculated against the reference value. So here I supply I use 200 milliamp as a reference. So if we go back to the plate voltage and curve plate voltage and current curve, we can see at 200 volt for a ideal 5U4 backend tube, the plate voltage is around 14 volt. So here we input 44. Okay, so actually what I input here is close to 41, and 41 actually is 41.5. And the reason I put 44 here is 5U4 is a directly heated tube, so the data sheet, this curve is measured between the plate and the center point of the heater. If this heater is AC, is supplied by AC power, this is 0. But here we use the DC power heater supply, so this point is 2.5 volts, so we need to add 2.5 to our test voltage. So that's why we had we put the 44 here instead of 41. Okay, so that's a setting for that's a measuring voltage we want to apply on the plate to get the 200 milliamp for a ideal 5U4, and we need to design the swing. The voltage swing is because we want to calculate the slope for rectifier, the around this region. So we need to we will send out two more voltages. One is 40 minus 5%, and the other point is minus 40 plus 5%. And at these 2 points, we can calculate the slope, and the inverse of the slope is the internal resistance. So so we configure we want a swing of 5%. Actually, I now I think 10% is more better. It's much better because 5% will give you more variation. 10% is will give you less variation. But anyways, so HV1 is configured at we take a measurement at 44 volt with a swing of 5%, and we're only interested in RP because rectifiers doesn't have a control grid, so we cannot derive Gn and mu from a rectifier. We turn on the HV2 link HV2 to HV1 100%, and we check the RP. We want to get the reading for the RP. So this is we are pretty much done with the quick scan setting. Now we need to provide the RP value for for the reference, and this value is normally not found in the data sheet, but it's so we need to derive the value from this curve again. So we can the way to derive it is we need to calculate the slope here. So we can pick 2 points around this 40 volt, the quiescent voltage. Let's say we pick 30 volt, and the current here is about 120 milliamp, and we also pick 50 volt, and the reference current is about 280 milliamp. So with these 2 points, we can calculate the slope. The inverse of the slope is the internal resistance by Ohm's law. So we can then put in the resistance here. Okay, so that's how we design a configuration file for rectifiers. So if we are testing it indirectly heated rectifiers, we need to connect ground to the cassette. Okay, and I think it's easy if you just follow the instruction on the PCB menu. Okay. What else? That's it. So okay, that's for designing a configuration file for rectifiers. Next time we're going to talk about how to design a configuration file for triads. See you next time. Bye.